In this segment, we'll examine the first half of the assembly from main from the primes.c program, as shown here. This will again be a guided tour, with ILQs asking you to think through your code on your own as much as you can, and then to comment as you go. So let's start with the first 7 instructions. And these set up the stack frame and initialize some of the locals, and they implement the initial declarations, the first 3 lines of the primeset.c code over here, separated out over here. So this is the most complex frame setup we've seen so far. Analyze it, please, and then answer the question below. The question is, how many bytes of local storage are there in the frame, and why that much? What are they used for? Can you determine the location of any of the local variables relative to FP? And what do you think occupies the top of the frame? Are any of the bytes left unused, as has been the case in some earlier stack frames? Well, after some analysis there, it looks as though 56 bytes are reserved, since we're increasing stack pointer by 56. And that, if you think about it, would be 40 bytes for prime set in particular. That array, 10 integers for each, 40 bytes. And then 16 more for the various other 4 integer variables. There's no unused space. From the stack frame code, it looks like nums to test is going into FP minus 20. We're obviously setting that to 320, so that's got to be nums to test. A brief aside, by the way, there, we have limited ourselves to 255 as a move constant before, but I mentioned obliquely that there are some larger ones possible, and this is the case. So we'll look at this in great detail later on when we analyze the machine language for ARM, but take it on faith for now that certain constants more than 255 are actually permitted. And I think we can deduce that total primes is at offset minus 8, since we're setting that to 0. This also then suggests that toTest and IDX are at minus 12 and minus 16, though we can't tell which is which till later in the code. And the fact that the int locals are all at the bottom of the frame suggests that the 40 bytes at the top of the frame are for the array prime set. So given that, please draw a diagram of the stack frame from bottom to top, every bit of it, and given the fact that array elements must go in increasing memory order, where exactly in that frame are prime set bracket 0 and prime set bracket 9? And here's a reasonable answer, as shown in the notes. The stack frame begins with the old frame pointer, and above that's LR. The total primes comes above that, set to 0. And we have a couple of unknowns, and then there's nums to test at 320, and then 40 bytes of prime set information with prime set 0 at the top. And the reason for that, again, is that the addresses increase from top to bottom, so the array indexes have to be in that order. I'm going to move that around a little bit. Okay, now let's look at the machine language for this first loop here in the C code. Question 2, question 3, I'm sorry, what assembly instructions implement this loop? Which instructions do the initializer, which do the incrementer, and which do the test? Recall from prior examples that the loop test may be at the bottom of the loop. And don't try to decipher the loop body at this point. Just identify it. We'll decipher it in a bit. Okay, so the answer here is that lines 21 through 37 implement the loop. And specifically, lines 21 through 23 initialize IDX, which apparently then is at offset minus 16. And we'll mark it that way in our diagram. Then line 23 jumps down to the test, which is on lines 35 through 37 here. The incrementer is on lines 31 through 33, right in here, just after the body, which is on lines 25 through 30. And let's do a brief note on the test, by the way. This does an IDX is less than or equal to 9 comparison. Note the BLE there. And that's logically the same as IDX is less than 10. Wherever possible, the compiler prefers smaller constants, since the range of constants is limited. Now, the loop body implementing prime set bracket IDX equals 0 needs careful discussion. And let's separate that out a little here. And so question 4. What expression do the first two instructions here compute and then leave in R3? Recall that IDX is at offset minus 16, as our diagram now shows. Write your expression using multiplication, not shift. And why would we want that multiplication? The answer is the ASL #2 shift is equivalent to multiplication by 4. So these lines put IDX times 4 into R3. This is the offset in bytes from the start of prime set to get to whichever index is indicated by prime set IDX, because each element of prime set is 4 bytes long. So now R3 holds the byte offset into prime set. As shown, the next 4 instructions from here to here put a 0 in prime set bracket index, but they do it in an odd way. Question 4. Assuming prime set starts at the top of the stack frame, at what offset from FP is its first element? At what offset from FP is prime set bracket 0, and why? And the answer is it's at offset minus 60, because we have to back up over the LR and then 56 bytes worth of local variables, including prime set itself. With this in mind, it's easier to see how those 4 lines work. The sub subtracts just 4 bytes from FP, leaving the result in R2. Then the add adds in the computed offset from R3, leaving that result in R3. And when we get to the stir, it's going to use that combined byte offset plus offsetting another minus 56. And that arrives then at the address FP minus 60 plus IDX times 4. And that's the location of the desired element of prime set. And the str stores a 0 there from R2. So question 6. That's pretty complicated, so why don't we rewrite those 4 lines so that the str needs no offset. And the answer here is that we could do a minus 60 right here on the first subtraction and then maintain the same add, and we could leave just R3 as the direct address of the desired array index. Again, just to be clear, R2 under this computation would contain the address of prime set 0. Adding in the offset R3 and putting it back in R3 gets us the address of prime set bracket IDX, and then we store to that address. Now this is intuitively simpler, but it has the disadvantage of requiring a larger constant, 60. Now that's not a problem in this case, but in general, if the compiler was able to reserve local space by subtracting a constant of at most 255, it wants to access variables in that local space using constants that are no larger. So it designs the array index in this kind of weird way that we saw before. As an exercise, question 7, write that array operation with just 3 instructions and without changing FP. So what we could do instead is rely on our indexing. We can get rid of this operation. We could then take an add to R3, that offset, FP. Now that hasn't done the minus 60 yet, but then all we have to do down here is put that minus 60 in as an offset, and we'll be done. But then again, that uses a constant that was larger than the one originally used to reserve the local space, minus 56. So for example, if local space had had a size of 252, we'd have to have a 256 here, and it would be larger than 255. The compiler then does this weird thing to avoid that. Okay, question 8. Now try rewriting it using just 3 instructions and no constant other than #0. And a hint, using SP will help. Okay, and the answer there is we could put in an add of R3 against SP, because SP is, of course, pointing to the top of stack, and that would immediately get us the right address anyway, and then we don't have to have any indexing here at all, and it's even better. Again, compilers are not all that smart when they're not optimizing, but soon we'll see them doing a better job. Okay, in the next segment, we'll look at the second big loop here in main and complete our discussion of the main code.